We'll get back to the idea of diagonalization and its applications starting in the next video, but before we do so, I want to talk about a very special type of matrix called a normal matrix that we have not yet seen. We have seen orthogonal matrices. I'll say a few things about that. I want to focus on this idea of a normal matrix and what that represents. So let's just remind ourselves the two basic properties that we have derived for a real symmetric matrix A. The first one was we found that the eigenvectors of A corresponding to distinct eigenvalues are always mutually orthogonal. Okay, so we could prove that, and we did. And then the second thing that we showed in the last video was that matrix A is diagonalizable using the modal matrix Q, which is comprised of the orthonormal eigenvectors of A. So Q transpose times A times Q will produce a diagonal matrix D with the eigenvalues down the diagonal. We call that the spectral theorem. It has to do with this diagonalization property. We call that the spectral theorem. And just remember this terminology that we also introduced earlier of a similarity transformation. Remember, a similarity transformation is a transformation such that the eigenvalues do not change. So that's the case here. A and D have the same eigenvalues. Remember, a diagonal matrix has the eigenvalues down the diagonal. So A and D both have the same eigenvalues. So Q transpose times A times Q, as well as the more general diagonalization procedure we'll talk about in the next video, are both similarity transformations. So if you remember, the reason why we focused on real symmetric matrices was because of their prevalence and applications. We see them all over the place in science and engineering, numerical methods, and so forth. So that's what motivated us to think about, are there any special property of real symmetric matrices that we should be aware of and that we can take advantage of? But the mathematician in us asked the question, well, but is a real symmetric matrix the most general matrix that has these very advantageous properties? And the answer is no, that's not the case. The most general matrix that has these properties is called a normal matrix. So a normal matrix is one that commutes with its conjugate transpose. So that means that the transpose of the complex conjugate of A times A is equal to A times the transpose of the complex conjugate of A. Now we're dealing mostly with real matrices here, so we can get rid of the complex conjugates, and so that would correspond to A transpose times A is equal to A times A transpose. Clearly, symmetric matrices are normal matrices, because a symmetric matrix is such that A and A transpose are the same, so then these products would be precisely the same. It's also the case that Hermitian matrices satisfy this form. Orthogonal matrices satisfy this, because an orthogonal matrix, Q transpose, is the same as Q inverse. So therefore, this would just be I. And this would also be I, the identity matrix. So it's true for orthogonal matrices. It's true for skew symmetric matrices, unitary, skew Hermitian matrices. Those are all normal matrices. But not all normal matrices fit into one of these categories. So there are more general matrices, normal matrices, that have these properties that don't fit into one of these nice categories. So given that these normal matrices have some special properties, namely the spectral theorem holds, Q transpose times A times Q gives us a diagonal matrix, as well as the fact that the eigenvectors are mutually orthogonal, it behooves us to take a look at these two products, A times A transpose and A transpose times A, and just see if there's anything particularly special about those two products. It turns out there is, and that's going to be a continuing theme throughout much of the rest of the book. So let's say A is any matrix now. So A is no longer real and symmetric. A is any m by n matrix. It doesn't even have to be square, so it's any matrix. Well, we'll assume it's real for now just to keep things nice. But so the first property, which is rather easy for us to convince ourselves of, is that A times A transpose and A transpose times A are both square. So if A is m by n, then A times A transpose, A is m by n, A transpose is n by m, so the result is going to be an m by n matrix, which of course is square. Likewise, A transpose times A transpose is n times m, A is m by n, so the product will be n by n. So they're both square. Okay, so that's useful. Now the second one is very powerful. Notice that, and we can show this very simply, that both of these products are symmetric. Remember, A is any real matrix, and it's not even square, it's n by n. But the products, A times A transpose and A transpose times A, are both symmetric. So let's see that very simply. So let's look at A times A transpose. Well, that's the same as the transpose of A times A transpose, because notice what happens here. Remember, the transpose of the product of two matrices is the product of the transposes in reverse order. So the transpose of A times A transpose will be A transpose transpose, which is just A, times A transpose. So A times A transpose and the transpose of A times A transpose are both the same. Therefore, these products, even though A is not symmetric, A times A transpose is symmetric, as well as A transpose times A. So this is really powerful, because now the properties that hold for symmetric matrices, we can apply not to A, but to A times A transpose and A transpose times A. This is going to be really significant in some applications that I'll mention in a moment. Another really useful property is the fact that both of these matrix products have the same non-zero eigenvalues. Now you notice they're not the same size. One is m by m, one is n by n. However, the non-zero eigenvalues are going to be in common for both. All of the additional eigenvalues are going to be 0. So if one is bigger than the other, then the smaller one would have up to n non-zero eigenvalues. The larger one will have the same n non-zero eigenvalues, and all the rest will be 0. So this is very useful for us as well. The matrix products are both positive semi-definite. So that means that all of the eigenvalues are non-negative. Now remember, we can't say anything about positive definiteness of A because it's not real and symmetric. But A times A transpose times A, those are symmetric. So we can talk about whether they're positive definite, or in this case, they are always positive semi-definite. And that's allowing for zero eigenvalues. If they don't have any 0 eigenvalues, then of course they're positive definite. Now, because both of these matrix products are symmetric, the eigenvectors are all mutually orthogonal. So this is huge because, again, remember how we've been using these mutually orthogonal eigenvectors in the last few videos. We're using them as the basis to solve a system of linear algebraic equations, the basis to use for this diagonalization process. So now, regardless of the A that doesn't have these nice properties, A times A transpose times A, both have these properties that we can now utilize in the same way that we have been. So we're going to encounter some really useful and powerful decompositions, such as singular value decomposition. You've heard me mention that a couple times. Polar decomposition is used in continuum mechanics quite frequently. Least squares methods, which are going to be used in part 3 for optimization. And then POD, which I've also mentioned a few times, which comes at the very end of the book in chapter 13. So all of these are going to take advantage of these facts that even though A may not have these properties, A times A transpose and A transpose times A do, and that's going to be the basis for a number of very important and useful operations and applications. Now the rest of this section I do an example and talk a little bit more about some of the ramifications of what we just discussed. But I just want to close this section with talking about one very important physical example in the context of stability. So remember, stability asks the question, for a given system, if you perturb it with a small perturbation, just give it a little tickle, what happens to the system? Does the amplitude of that perturbation grow and become unstable, or does it get damped out and the system remains unstable? This is discussed more in depth in chapter 5 of the book. We'll get to that later. But I just want to give you a little preview of what difference it makes if the system is normal versus non-normal. If a system is normal, then the stability question, which is a physical question, is answered solely by what are the eigenvalues of the matrix that defines that system. And the values of those eigenvalues determine the behavior of the stability. of a normal system. If the system is non-normal, those eigenvalues define what happens as t goes to infinity, whether they're stable or unstable, so they decay or grow. But they don't tell you what happens in intermediate times, order 1 times, before we get to that long time asymptotic stability behavior. So that's called transient growth. It's asking the question, in those early order 1 times, say you have an eigenvalue that says it decays, so everything is stable. But in that order 1 time for a non-normal system, it's possible you could get this transient growth of these amplitudes before it dies down. And what happens to those? So maybe the system is such that it becomes nonlinear, additional physics come in, and it never even gets to that t going to infinity asymptotic stability state. A good reference for this, there's a little bit more in this book, but there's more as well in the Variational Methods book that goes into a little bit more detail, gives some really interesting applications and examples, some simple ones and some from fluid mechanics that illustrate this transient growth phenomenon, which is very important to be aware of. The rest of the section I'm not going to go over in detail, but it's focused on some of the properties of orthogonal matrices. So we said, for example, that an orthogonal matrix is such that Q transpose is equal to Q inverse. So that's actually proven here. So if you're interested in seeing a proof, you can see that. We also show that the determinant of an orthogonal matrix is always plus or minus 1. And what that means, it behaves nicely. So of course it's never 0, and it's never huge, and it's always nicely behaved in that sense. It also turns out that the rotation matrices that we discussed in chapter 1 are orthogonal. So any matrix that does a rotation is an orthogonal matrix. We also prove here that the eigenvalues of an orthogonal matrix are always plus or minus 1. And again, that has implications for operations that are using these matrices, because the eigenvalues are order 1, they're never too small, they're never too big. Condition numbers, therefore, are very well behaved. And so we like to work with orthogonal matrices when we can.